So happy International Women's Day to all of you that choose to celebrate that. It's a pretty big deal. Like worldwide, like it's a really big deal. Much more so than it is here, but I love it too. All right, what we're going to do today, let me just tell you a couple things. In just a minute, I'm going to give you a second to hand in your pendulum lab. But let me have your actual attention up here for just a minute. Let me have your actual attention. Then I'll give you like 2 minutes to finish up what you need to finish up. Listen to me for just a minute, okay? Just so I can tell you the plan and kind of where we're at. And then, like I said, I'll give you a couple of minutes to work. So you're going to hand in your pendulum lab in just a minute. I want to tell you about a couple of events that are coming up. First of all, I just got the email about Spirit Days next week. Spirit Days for celebrating spring break. I guess, I don't know. But the reason I wanted to tell you about this is because I don't want you to miss out on the opportunity to have pajamas on Monday. Like that was my big concern, is like that would be unfortunate if you come to school with regular clothes on, not knowing that it's PJ day on Monday. And then the rest of it, you can, follow through and figure out what you need to do. Crazy socks on Thursday. Pretty psyched about that. So that's, anyway, just FYI about that. The other thing, I just got information about a fantastic opportunity. If you are free next Friday, so the first Friday of spring break, the physics and astronomy department at the University of Iowa puts on a really, really good demo show. And sometimes people are like, wow, that seems really nerdy. But I will tell you, like, non-physics people love this. Like, they put on a very, very good show. It's an hour from 7 to 8. It's in Van Allen Hall downtown. And I know the guy that's in charge of all of the demo stuff for the physics department. He and I are friends. We've known each other for a long, long time. Anyway, it's going to be really good. So find a friend, take them to see some physics, and then, go do something else. But strongly recommend it. I'll put this up again so you don't forget and don't, miss out. But they'll do some good stuff. It'll be fun. Question? Did you have a question, Alec? No? Okay. But anyway, next Friday, if you don't have anything to do, it's an hour of your life, and it'll be well worth it, I'm sure. So anyway, 2 opportunities for some, excitement in your life, I guess. We are going to, I'll give you 5 minutes to get everything done that you need to get done for your pendulum lab if it's not already turned in, okay? Then we're going to do the wave words, and we'll do a couple examples. I think we're just going to not do this lab, but we'll see. We won't get to it today, I don't think. I did want to draw your attention to the homework that is on Canvas. These assignments here are things that that have been assigned in the last couple of days, whether you knew it or not. So I want to make sure that you see that. And then there are some homework problems for Monday. The reason I'm drawing your attention to that is because Monday we're planning to go over homework. Monday we're planning to review. And then Tuesday we're going to quiz right away, boom, over the beginnings of this wave business. Okay? So whether you're surprised about that or not, we are going to do that. I want to get it done before we get too far into, it's almost spring break, it's almost spring. And then we'll do some more stuff. We're not done with the unit. We're just done with this first kind of basics definition section. Yeah.
Is next week the last week of school?
Before spring break.
Yeah.
Yeah. Is that okay?
Yeah.
Okay. Ding. Delay happened. All right. So what can you do right now? You can turn your pendulum lab in if you need to talk to somebody or need to ask me a question. That's what you should do. There are 3 pieces that you should give me. The yellow sheet, the green sheet, the gray sheet. Okay? That goes up in my basket. We'll regroup in a minute. Boom. All right. So you have that yellow wave word sheet in front of you. And as I said to you earlier, the quiz is mostly going to be over. A lot of it's just definitions. The reason that I didn't want to do this just is because it really is just so we're just going to go through the notes really quick. Okay, then we're going to go out and see some of it, and then we'll do a couple problems. It'll be great. So here we go. There are 2 fundamental ways to transmit energy or information. One is by transferring matter. So if you think about, if I needed to tell Josie something, okay, or if I needed to let her know something, what's a way that I could do that?
Tell her.
I could tell her, right? And so let's think about the physics of what's going on. If I tell her my body has to vibrate my vocal cords, are you with me there? So I got these vocal folds inside my neck, or inside, right here, and they're vibrating. That's making the air right here vibrate? And then is the air right in front of my mouth actually moving to her ear?
No.
No, it's not. It's moving air, and it's moving air, and it's moving air that gets to her ear. Does that make sense? Okay. How else could I give her some information? I could write it on a piece of paper, right? Crumple it up and throw it at her. And if I did that, I would be literally sending that information. You with me there, right? Then I'm transferring matter, okay? If I talk to her, though, I'm not transferring matter. What am I transferring, or what am I sending? What is it? I'm sending a wave, yeah. Yeah. Unlike in transferring matter, this approach does not result in any permanent displacement of the surroundings. So unlike when you're doing a fill-in-the-blank worksheet for all of your years of life, because I did them a lot too when I was in middle school and some in high school too, you fill it out and you don't really read anything. All you want to know is what word goes in that blank, right? Well, it's like, yeah, of course. That's not how this works. I'm transmitting information to you via matter, and I want to make sure that you know this. So you may want to underline that or note that in some way, okay, that does not result in permanent displacement of the surroundings. So if I'm going to tell Alex something and I move my vocal cords, and my vocal cords then start to move the air, okay, 35 seconds later, 2 minutes later, do you have any evidence that I have sent Alex information in that way? No. Now, if I wrote it down and I crumpled it up and I threw it at him, would you have evidence? Yeah, there'd be a note, right? A note that actually has that information. But when I'm sending a wave, there's no permanent displacement of the surroundings. That air just bounces back and forth and then it's done. What's up, Jacob?
What about the people that sing and then break the glasses?
Right. So in that case, that's a really good question. So you're sending a wave, and that part is not permanent, right? But if that wave then comes into contact with something that has the same frequency, the same natural frequency, then it can cause that thing to shatter, right? So that part, I suppose, are you arguing that would be permanent damage? Is that what you're... Yeah, I mean, that's it would happen, but that's not, I mean, it is because of the wave, but there's a little bit more physics there to it. Is that fair? Okay. Cool. All right, that's number one. Number two, or bullet point number two. While the energy is being transmitted, right, the information that I'm saying to Courtney is being transmitted, she can hear me, the blank, the material through which the wave travels, is temporarily disturbed. What is that? The blank. What goes in there? What is it? The medium. Yes. So the medium is the material. What is the medium through which my voice is traveling? Air, right? If there were no air, there would be no transmission of sound. It's not possible. You can't do it. Okay? So when you watch those silly old sci-fi movies and the person is in their, they're doing a spacewalk or something and then they, lose their tether and they just start screaming, who hears them? No one is there to hear you scream. And there's no air to transmit that information. So you can scream and your vocal cords can move. Right? So everybody put your hand right here, and then say something or sing something or whatever. That's so pretty. Do you hear or do you feel how it vibrates? Can you feel that? Right? It's vibrating the air because your vocal folds are literally just vibrate. They're just pushing on the air, right? But that air has to be there to be disturbed. Okay?
So how do they talk in the movies?
It's a movie.
Don't they got radios?
Well, sure. And that's the thing. So if you have one astronaut, right? And so inside the astronaut suit, there's air. Because, oh yeah, if you were out in space and you didn't have a suit on, you would have bigger problems with the fact that you can't scream. Or that screaming isn't going to do any good. Because, lungs collapsing, vacuum, like there are bigger issues. Okay? So we have to understand that we're in a pressurized situation. So then if you talk, right, then there's a little microphone, and that microphone picks that up, and it makes it an electrical signal. Then that electrical signal is probably converted to a light signal that's transmitted to the other person. Unless you have a tether between the two of you, then it might just be electrical.
Like cans?
Like cans, yes. The string between the two cans, is that what you're talking about? Yeah, tin can phones? I want to make sure we're on the same, okay, cool, yeah. So if you're doing that, the medium through which that sound is traveling is the string, yes.
So that works?
Sure. Have you never tried that?
No.
Come on! That's a project for you. Well, tomorrow you can do that, yes.
Okay.
Get it?
Oh, wait.
You're welcome. But yes, try it out tomorrow and then let me know how it goes.
Okay.
Yeah, we'll see like pictures and all that'll be great. All right. Wow, that was cool. All right. So when this medium is oscillating, it can do one of two things. There's open bullet number 1 and open number 2. The key word here, the key difference is this word right here. Hopefully you found this in the book. Yeah? When a medium, so that means the stuff, oscillates perpendicular to the direction of wave motion. So what in the world does that mean? It means if I have a string, and we're going to go out and do this in just a minute, okay? And my wave is moving in this direction, then as that wave moves, the particle that I've got on my string is going to move perpendicular to the wave motion. Which way is that? Is that this way or this way? This way or this way, right? It's going to move up or down. Yeah, so it's going to go something like that. Okay? When the medium oscillates perpendicular to the direction of the wave motion, so that means that this thing is going like this, okay? What kind of a wave is that? Did you write it down? It's transverse. The easiest way to remember this is that if instead of writing transverse with a little t, you write it with a capital T, and you flip it over, what does it look like? It's a perpendicular sign. So the transverse wave is one when the medium is moving perpendicular to the wave motion. Okay? So if you can just get in your head, transverse, perpendicular, you're going to be golden. Okay? Some examples of transverse waves. Did you find some in the book? I think they probably told you a couple. Does anybody know? If not, you're just going to have to start guessing. What kind of waves have you heard of? Two big ones. Yeah. Sound waves. Good guess. That's actually the opposite kind, so I'm going to write it down here because it is the other one. And it's kind of a 50-50 shot, right? But we'll talk about why that's true, and I'm glad that you were willing to give that a go. We'll talk about exactly why sound actually goes down here in just a second. Okay? So go ahead and write that one down there because we'll come back to it. When we're talking about transverse waves, and again, it's kind of a 50-50 shot. Got this or got this. What other kind of waves have you heard of besides sound waves? Microwaves. Now, are you talking about the appliance or the actual wave? The actual wave. Okay, so microwaves, sure, they are transverse waves. But microwaves are just a type of what kind of wave? Does anybody know? Do you see it over there on that poster, Cassidy? Do you see microwaves written down?
Yeah.
Yeah, and what is that poster labeled as? Electromagnetic, yeah. And we'll get into that piece of it later. Yeah, we'll get into that piece in a couple weeks because of spring break. Electromagnetic. So that's the fancy word that when your parent walks, you walk in tonight and you're like, they say, what'd you do at school today? You're going to say that, right? I learned a new word. I learned about electromagnetic waves. That sounds really fancy. And then they'll be like, ooh, that's exciting. And then you're going to know that electromagnetic really just means what? What's electromagnetic just a super fancy word for? Does anybody know? Super fancy word for light. Yes. What's that? You knew it? Cool. That's awesome. Or you saw it on a poster or something like that. That's okay too. Yeah. But all light waves. So that includes microwaves, and that includes radio waves, and that includes visible light, and that includes all those things. And we're going to talk about those in a little while. Okay? But you can know that all light waves are transverse. Okay? All light waves are transverse. Yeah?
Is that what you said when you were talking about the astronauts? You said the electric turning to is transferring to
Electromagnetic. Yep. It would turn into radio. A radio signal. Yep, absolutely. Any other examples of transverse waves that you can think of from experience? So these are ones that go up and down and up and down and up and down like this. Ideas?
Shock? Like a shock wave? I don't know. I've heard that before, but I don't actually know what it is.
Okay, well, I was just going to ask you, I was going to say, what do you mean by shock wave? Because there are lots of different ways that one could talk about a shock wave.
I just heard it in science
Okay. Okay. So generally when I think of a shock wave, I think of like an airplane moving at faster than the speed of sound. And if that's the case, then it's a sound wave. Does that make sense? But there are some other kind of shock waves that you may argue are transverse. Does that make sense? But so it kind of depends on what way you say it. Yeah. Have you ever made waves before?
Yes.
When have you made waves?
In the water.
Oh! And you laugh, but it's true, because that's where I was thinking about it. Absolutely. If you splash like this, think about it. Right? If you splash like this, you're making the water go where? Up and down. But does the water, does the wave rise up out of the water? Does it travel this way? No, where does it travel? So you go like this and you make the water go like this and it goes this way. That means that they're moving perpendicular to one another, right? You could also think about it like a really still pond. If you drop a rock in it, you with me there? And you see that whoop, 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 the ripples? Absolutely, that's a transverse wave as well. Yeah?
what are those things that people in the gym or the ropes they go like that? I don't know.
Yeah. Like with the like that. Yeah. I don't know what that's called. But that is absolutely another example of, does anybody know what that's called? Anybody? Ropes. We'll write it down.
Okay.
So we got light waves. We've got ropes. What's that? Is it just called? I don't know. I'm not super cool like that. Water waves. So surface water waves. And the other one that I was going to give you an example of, and some of you may have heard of this in middle school or maybe in freshman year, if you were talking about earthquakes, when the earth shakes, it creates actually two kinds of waves, P waves and S waves. I don't know if you've ever heard of that, if that means anything to you. The primary and secondary waves, the S waves, which are the secondary waves, are also transverse waves. They're closer to the surface. Has anybody ever experienced an earthquake before? In here? Yeah. Did you feel like multiple, like you felt like one set and then another set, or no? Yeah, right. I felt it. Yeah. I was like, whoa, what's going on? And it wasn't very strong. But generally, that's the only earthquake I can speak to either. But my understanding is generally when an earthquake travels from the epicenter out, you actually feel one like main rumbling, and then you feel another one that's not an aftershock, but it's actually part of the same earthquake. And that is the S wave, the secondary wave that comes out. And that's more of a surface wave. The other one is deep underneath the ground. So there you go. New information for your day. All right. Let's draw a sketch of a transverse wave. Okay. A transverse wave is the wave that like you always think of when you're thinking of a wave. Okay. So the wave is traveling in this direction. Okay. But again, the object is moving in this direction. We can label a couple of things on the wave, a couple of things that you can measure on the wave. Friends, if you're going to be chit-chatting, then I'm going to have you switch spots, okay? Thank you so much. It's just super distracting to me. The maximum distance on a wave from, what is this line? Equilibrium. Let's label that line. The maximum distance from the equilibrium to the wave, this distance here is called the, we've talked about it already, amplitude, yeah. Okay. These two I'm not really keen on, but I am going to tell you them just so that if you see them somewhere, you feel informed. Generally, they talk about high points above the equilibrium as crests and low points below the equilibrium as trough or troughs. It's spelled kind of funny, so people always want to call it like troghs, but it's trough, like it's the thing that a pig would eat out of at a farm. Does that make sense? Okay, it's like a trough. Okay. From my perspective, I don't care if it's a crest or a trough. It is a maximum distance, the same distance away from the equilibrium in either case. The nice thing about waves is that they're always symmetrical. Okay. We'll come back and add one more thing to that in a little bit, but right now I'm going to leave it where it is. On the other hand, so the first one was a medium oscillating perpendicular to the direction of the wave motion. That's transverse. It says, on the other hand, what kind of wave is this, friends? Did you write it down? Longitudinal. A longitudinal wave is one in which the medium moves parallel to the direction of travel. Again, the key word there is parallel. So I had the little trick to remember that transverse was perpendicular because you take the T and flip it over, right? For this one, the trick is, what does longitudinal start with? And what does longitudinal end with? And if you put those two L's together, then you get something that looks a whole lot like parallel. Okay? So that's the other piece of the hint there. So the big example for longitudinal waves are sound waves. Okay? And we'll get out some tuning forks in a little bit, or not today, but in a few days, so you can really see how that works. But literally, when sound is coming out, whether it's out of your vocal cords, right, or out of a tuning fork, or out of an instrument, or out of whatever, it's pushing the air like this, okay? And that air, as it comes to you then, vibrates your eardrum, and that's what your body then translates into an electrical signal that you hear as sound. Okay? So sound is absolutely, that's like the number one best example of a longitudinal wave. Any other ideas of things that might be longitudinal waves? You could look up at the top and see if you can think of anything that might be related, not ropes so much. Does water sometimes move down deep?
Yeah.
Deep water waves, way down at the bottom of a deep lake or an ocean. Okay. Those are longitudinal waves. That kind of makes sense. They're getting pushed out, out, out. And the other really good example of longitudinal waves are the earthquake, the P waves, which are the primary. The primary waves that move through the mantle, okay, of the earth, okay, in that magma, they move longitudinally as well. Well, a transverse wave is really easy to draw. Longitudinal, not so much, but let's give it a shot. A longitudinal wave, I generally draw this one as if it's going through a slinky, which we'll see outside in just a couple minutes, but I just want you to kind of see and imagine here. So there's the slinky, it's kind of pushed together. I'm going to spread it apart, squish it together, spread it apart. Yeah, it's kind of hard to draw, right? I've been practicing for a few years. Okay. So you got the part where it's got high pressure, where it's squished together, and then you've got the part in the middle where it's not. And those little distinctions are the part of the wave. So this part here is called a compression. That's high pressure. Then the part where it's really spread out in between. This is the strangest word that you're going to have to know. Actually, you don't even really have to know it, but I'm just letting you know what it is because it's, I don't know, interesting or something. The word is rarefaction. Rarefaction. Compression and rarefaction. Okay. And in between them, you get your points of equilibrium. Okay. How are we doing so far? Are we okay? Okay. I'm going to pause this for a minute. You can leave your pencils where you're at. You can leave those papers where you're at. We're going to go out in the hall and just see all this stuff real quick, and then we'll come back and do the back. All right, my friends. So now that we've seen a bunch of that stuff, we need to write a couple more things down. Oh, I guess we didn't really talk about this, but we're going to talk about it right now. When sending information via a particle or a wave, the transmission is not instantaneous. It's important to know that it takes a while. It did take time after I sent that information down to Zach for it to get to you, right? It wasn't like it was boom, it's there. It took time. The amount of time that it takes is dependent on the type of medium that you've got and some other things as well. The velocity of a wave, so this is like the thing that you want to put a box around here. The velocity of a wave is equal to, well, some stuff, right? This funny letter is a Greek letter. Anybody know the name of it? Lambda. Lambda is the way that you spell the pronunciation of that Greek letter. Lambda. Say it with me. Lambda. Lambda. Yeah. Lambda represents the, did anybody get this from the reading? The wavelength. Lambda represents the wavelength, or the distance that a wave travels in a complete cycle. The distance that a wave travels in a complete cycle. I'm going to go back to the other side real quick. or maybe it's not to the other side because you guys are on the same page, sorry. A complete cycle is from crest to crest, or from trough to trough, or from one point in the cycle to the next point where a cycle has gone through. In either case, that is lambda, the wavelength. It's kind of like an upside down and turned around Y. If you need like a little, like, how do you write that thing? Flip it over. Is that right? Is it just flipped over? Yeah, just be flipped over. Okay. Lambda is a length. It's a distance. So what's it going to be measured in?
Meters.
Yeah, just like anything else, right? Big T is the period. What's the period of a wave? We talked about this already because it's the same as it is for the pendulum. What is period? The time
It takes
for,
it to do one.
yeah, same, right? Time it takes to complete one cycle. Okay, and it's measured in seconds. So this equation might look a little bit scary, friends, but it's really not, because you know that velocity from way back in what, September? Whenever we did velocity for the very first time, velocity is just what over what, friends? Distance over time. And this distance is just the distance the wave travels in a cycle. And this time is just the time it takes for a cycle. You with me there? So really it's just a distance over time. It's just a special distance over a special time in both cases for one cycle. Sometimes, though, we don't like denominators. We've been through this a few times, right? We don't like denominators. So instead of using that over t, we're going to use something else. What are we going to use? We can say that v is equal to lambda times. What letters do we know? F. Okay. And F is the frequency. Okay. The frequency is the number of vibrations in a given time. So period is the amount of time for a cycle. Frequency is the number of cycles in a time. Do you see how they're kind of like opposites? In fact, they're inverses. We'll write this down because it's good to know. Frequency is equal to 1 over period, or by the same logic, you could say that period is equal to 1 over frequency. Okay. If we look at the units, period is measured in seconds. So this is 1 over seconds. Frequency is measured in hertz. Hertz is just 1 over seconds. That's all it is. Hertz is literally just 1 hertz equals 1 over seconds. That's all it is. Nothing special or fancy with that. Okay? On your homework for Monday, there are a couple of problems that deal with this equation. Given all of the scary equations that we've done this year, this one's pretty straightforward, don't you think? If you're given a lambda and a period, you can find v and kind of mix that all up together. Okay? We're going to cruise through and get these last few done. We went through this when we were out in the hall. Unlike matter, waves can or cannot occupy the same space at the same time.
Yes.
Yes, they can. Oops. My stylus is just done for the week. When two waves meet, they undergo superposition. Circle that, highlight that, make a mark around that. It's an important word, superposition, in which the total amplitude of two or more waves in the same space is the blank of their original amplitudes. What do you think we do with the amplitudes when they go together?
Add them.
We add them, yeah. It's the sum. So you got a little one going this way. And you got a big one going this way. Let's say this one has an amplitude of 2. This one has an amplitude of 1. What's the amplitude going to be when they interact? 3! Yay, because we can add, right? Yay for us. And I don't mean that in a sassy way. I mean that in like a literally, yes, that's all you're going to do. That's just going to be 3. And then after that, that 2 wave is going to go on its way this way. And that 1 wave is going to go on its way that way. And life is good. Okay. It's important to note that the combination that's known as blank only occurs for an instant. What is that word that you put in there? Anybody know? Starts with an I. Interference only occurs for an instant. There are 2 different types. We can separate them into 2 types. One is when the disturbances are on the same side and it increases the amplitude. What do we call that one? Look at your list if you haven't done so already. Constructive. Destructive you can figure out because it's going to be the opposite stuff, right?
Yes, ma'am.
Opposite sides of the equilibrium, decrease in amplitude. All right, my friends, have a fantastic weekend. I will see you on Monday. We will be going over lots of homework, so do your homework this weekend. All right? Have a good day.